Hello, everyone, or rather, Dobro dan, Praha. My name, as Justin said, is John Mertens, and I'm a principal engineer at change.org, and I'm here to talk to you about our experience using Elixir, specifically GenStage and its lovely abstraction flow, and lessons that we have learned from pumping a ton of data through it. Now, for those of you that don't know, what Change is, we are a platform for social change. People from all over the world come to our site to start movements on all topics and of all sizes. From two Canadian girls getting Starbucks to make a more environmentally friendly cup, to ending the taxes on feminine hygiene products, to fans building support to save their favorite shows. Our site's usually where I find out that shows got canceled. To people trying to make memes real. I definitely signed that one. Okay, on to the Elixir. Slowly. All right, technologically, Change is primarily built in Ruby and JavaScript, but we started using Elixir in early 2018 to build a high-volume, mission-critical data processing pipeline. And now, I won't go into too much detail on our adoption story. That's not why we're here. But suffice it to say that during all the early stage meetings about building this new system, someone kept bringing up Elixir and how it had this amazing library flow, and it seemed like it would be a perfect fit. So we built some proofs of concept in a few different languages and paradigms, and then we put them against each other with the two main criteria being performance and developer happiness. And after a few rounds, Elixir was the clear winner on both categories. Yay! Okay, so I'll get as granular as I'm allowed to when it comes to the details of our system, but the general flow is like this. Something happens on change.org. A petition is signed, a campaign update goes out, a victory is declared, something. And in usual distributed system fashion, there's an event log and a message bus and yada, 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 and in specific cases, an event gets added to a queue. Now, our Elixir system pulls these messages off the queue, preps them, transforms them, does some business logic, generates some side effects, and then depending on how everything goes, the message is either passed on to another system, or it's discarded or retried. And so far, everything has gone swimmingly. Sure, there have been a few hiccups, but no showstoppers. And while I would love to say that was solely due to my top-notch team, that would only be half true, which brings me to the first lesson that we learned with Flow. Let Flow do the work. Flow and GenStage beneath it, they're pretty amazing libraries, and they provide a few game-changing features by default. And so let me dig into a couple of those. Parallelism. Parallelism is awesome, especially in large-scale data processing pipelines. And now while parallel processing has always been possible in Elixir, Flow's abstractions make utilizing it a no-brainer. You can write code that looks essentially like your standard Elixir pipeline, and then when you run it, you can be sure that it utilizes all of your CPU cores. Now, I will now illustrate this with a totally contrived code example of what I mean. As you can see here, we are building an infinite stream of the numbers 1 through 5 and then squaring them. And now if you pop open an IEX shell and run this and then open an observer window, you get something like this. And you can see that only one scheduler is working on it. The green line is the one in question. I'm not good at Photoshop, so the orange one's still up there. That's actually the observer process. But if you do run it locally, be sure to kill it, because there's no end, and it will just eventually eat up all your memory. Now, here is that same code rewritten with Flow. And if we pop open an observer window while that's running, you can see on Observer that all the schedules are working. Look at all those reduction, GenStage, and init things going on the bottom there. Now the point of this example is that you can write the data processing pipelines the same way you'd write your normal Elixir processes, although now the work is automatically spread across all of your CPU cores. So I feel like everyone's on board for parallelism. So I'm going to move on to another fantastic feature of Flow. Back pressure out of the box. Now this is where a lot of people that watched José's talk yesterday are going to be primed for this. We have some overlap in this area. And so I'll say that technically back pressure is a feature of GenStage, but Flow is an abstraction over GenStage. So I'm going to count it. And then, I mean, just for context, every time I talk about Flow in this, I mean internally in your head translated to Flow and GenStage. But for those of you unfamiliar with back pressure or weren't listening to José yesterday, it's where your system asks for more data to process instead of data being pushed onto it. Now, back pressure is one of those features that I personally didn't totally realize how great it was until I was reminded of one of the main problems in systems without it. DDoSing yourself. If you come from a Ruby background like me, then you're probably familiar with using systems like Sidekick or Rescue to process data in the background. Now imagine, it's happened to me too many times. Suppose you're in a system like that and you get a sudden influx of events. So you either are in a situation where the queues are too backed up and you need to spin up more workers to handle those, or you are just generally over-provisioned on workers and they start chewing through it really fast. And those workers then start to overload your dependent systems. And before you get a chance to spin those up, bam, you just DDoS yourself, the site's down, no one's happy, pagers go off, it's a pain. So to be honest, after working with Elixir for a while now, I'd actually forgotten about the old self-DOS until I recently saw this Slack message at work. The backfill that this person is talking about, it's running in a Sidekick-based system, and the person posting this message is doing the current best practice, which is to do a little math up front, monitor the situation, and keep the DevOps team in the loop. There's got to be a better way, right? There's like 5 humans involved in that process. That's way too many. With Flow, your data processing is in charge of requesting more events, not the other way around. This means that if your process is dependent on some other service and that service becomes slow, your whole flow just slows down accordingly and no service gets overloaded with requests, so the whole system stays up. When the dependent system comes back up, you just follow it right back up. Now in our system, for example, we regularly increase the volume of data going through by adding new types of data to process. So it's essentially just like a stepwise change as a whole new section of data goes flooding in. And each time we do it, it's just YOLO. Like we just turn it on and we don't worry about knocking over any dependent systems. It's pretty fantastic. Okay, so now we know some of the great let flow do the work features. Let's talk about how we make sure that our code is set up to take advantage of them. So the next lesson, organize your flow. I just want to touch on a couple of things that fall under the broader topic of just stop for a minute, take the time to organize your flow. What do I mean by this? Specifically, keep your flow simple. Flow and GenStage are powerful libraries that enable you to do some pretty powerful data pipelining gymnastics, but I'd recommend at least starting simple and then only increasing the complexity as the constraints of your system require it. The more straightforward and simple you can make this flow, the easier it's going to be to reason about and debug and all those great things. And I really like this quote from the Flow documentation. It describes this concept of embarrassingly parallel problems. And to me, it highlights the state that we should strive to get our processing to. So the big takeaway is that if you can shape your problem into an embarrassingly parallel problem, then Flow can really shine. Now in these same Flow docs, just a little farther down, there's a section called Performance Discussions, and the first suggestion in it says know your code. And then it proceeds to describe a handful of problem-specific optimizations that you can make to the canonical word counting example that's in the docs. But I think that know your code advice can also extend to the rest of your system. I mean, for good or ill, we're all basically building distributed systems now. So it would behoove us to keep all parts of our system, or at least the adjacent ones, in mind when building this. This understanding of one's system will pop up a few more times in this talk. Now in our particular case, we use SQS for queuing, so as you'll see, we take that into account when we build our flow pipelines. Okay, with this in mind, let's take a look at some code. Psych. First, I want to give a quick background on SQS for those who haven't worked with it before. This isn't a pitch for SQS, but I'm about to show you some code that makes some assumptions based on the fact that SQS is our queue. So this is totally in the spirit of understanding one system. So real quickly, SQS, or the Simple Queue Service, it's a service in the Amazon ecosystem. They have a bunch of features, but the two I wanted to mention real briefly are the concepts of a visibility window and acknowledgements. And it's helpful, José talked about acknowledgements a little bit yesterday. So it works like this. When you pull a message off a queue, you have a set amount of time to acknowledge that you've received and processed that message, and that amount of time is called the visibility window. And that's configurable. Now what happens if you don't acknowledge the message within the visibility window? It goes back into the queue. Now if a message is pulled and not acknowledged like a given number of times or configured number of times, then it is either discarded or sent to a dead letter queue, depending on how you set it up. Okay, thank you for humoring me. That was all the background you should need for this. Let's now take a look at a flow. So here is an example of a flow that we use in production, although I have changed the function names to protect the innocent. I pulled out a few things that are not relevant to this talk. But it seems pretty simple, right? So I'm going to do a quick walkthrough of what's going on here so we can have some context for the rest of the talk. Now in our setup, we have a custom GenStage producer which can pull messages from SQS. And when the app boots, we spin up a configurable number of these producers, and then this function just grabs all those PIDs and feeds them into the flow from stages to sort of be the top of the flow. And this sort of middle section here is the part that should look most familiar to folk. We could swap out flow for Enum, and this would look like your standard Elixir pipeline. And this is where basically all of the application-specific code gets executed. And as you can see by my lovely function naming, for each SQS message coming in, we prep it, which is mostly just turning it in from the JSON string that comes in into our specific data structure, which I'm going to talk about in a minute. And we basically run that message through some business logic, also known as like making decisions. Then we commit any side effects that are built up in those transformations, which are usually database writes. And then finally, we log any errors that have come up along the way. I know, logging errors is a side effect too, but organizationally it made sense as two different functions. And before I go on to the third step of the flow, I just want to point out that this code here is functionally equivalent to this code. And actually under the hood, flow merges all those mappers together. And I just like to bring that up because I think I'd been using flow like 10 months before I learned that was actually happening. Anyway, continuing along. In the final step here, we partition the messages by the window, which is defined in that commented out code above. Then we reduce that partition with our ACK accumulator function, which I'll speak about in a second. But essentially what this function is, what all this code is doing is saying every 10 messages or every 5 seconds, whichever happens first, batch up the messages, send them to the ACK messages function, and then reset the flow's internal accumulator. Why only 10 messages? Remember when I said that one should understand your own system? That's coming into play here. All the batch endpoints in SQS are limited to 10 messages per batch, so we are limited to 10 messages per batch. So you see that kind of throughout this. Now if you're like me, and hopefully you're not, but kind of, you might have a little voice in your head that looks at this code and says, now hold on, Buster. That looks too simple to do any real work. There ain't even any conditional branching. And I would say, aha, thank you, old-timey programmer voice cowboy in my head. Good point. That brings me to the next section in the Organize Your Flow lesson, which is to use a token. The key that keeps our flows simple has been to use a consistent data structure, or a token, if you will, throughout the pipeline. The data structure most essential to our flow is the, again, brilliantly named message struct. This is a struct we use through the whole pipeline. The first thing we do when a message comes in from SQS is we create a message struct based on it. You can think about it like plug.con or like an ecto change set. It gets passed through the flow, getting transformed along the way. And now the consistency of having the same data structure at every step in the flow is how we can keep it so simple. And after listening to Brooks talk, I feel like it's a little monadic. Let me put up some code so I can elaborate. This is basically what we have in production, but whittled down to the fewest parts. The status property is does what it says on the tin. It just holds the status of the message, defaulting to the very common OK atom. The message type is a string identifier of the specific message that we are processing, specific type of message we're processing. And now the combination of the status and the message type are how it gives us a mechanism for flow control, which I'll touch on next. The body is basically a map representation of what came in off of SQS. It's useful 4 times throughout the process when we need to reach in and pull out message type specific data. And then the status metadata is just another map, and we can use it to store arbitrary bits about the message status. For example, maybe our message errored, and we want to know why. That's a good place to put it. Okay, here is an example of how we can handle different types of data while keeping the flow simple. Thanks to pattern matching, we can define a different version of the handler for each type of message we need. The only requirement is that it adhere to the contract of a message struct comes in, a message struct goes out, which you can see the type spec at the top. And you can see here we've got like a click message type and a sign message type and so on. So there are probably some very clever folk here thinking that adding new function definitions for each type of data that we're processing is going to get messy as the number of message types grows. The file's just going to get bigger and bigger. And you clever people would be correct. But if you squint to this code a little bit, you can see how we could extract out some message type specific code. We could put those in their own modules, and we could sprinkle a little metaprogramming back to tie it all back together, which is actually a thing I just did recently, and it has made adding new messages to the system way easier. But John, you ask, what happens when something goes wrong? Good question, John. Inevitably, something is going to go wrong, and we're trying to process this message. Either somehow bad data gets in, or a database is unreachable, something. In those cases, our process is usually to catch the error, or usually match on the error tuple, switch the status field of the message to the error atom, and then put the reason in the status metadata map that I was talking about, and then pass that transform message down through the flow. And this works because, I'm going to put this code back up here, and you can see the top 2 functions both match on status of OK. But the final one just takes whatever gets to it and passes it through, unmolested. And we set up all of those top-level mappers that I was showing you earlier in that same way. So anything errors out, it just falls through. And then in our sort of that consumer section near the bottom, we reduce our batch with the accumulator function, which is just a simple thing that filters out messages that have an error status. So anything that doesn't have an error status gets sent through here. And to step back for a second, the point of this partition reduction is essentially to batch no greater than 10 messages that we're going to then acknowledge to SQS to say that we're done processing. And again, since we know our system, we know that any messages that got this far and isn't acknowledged is going to get put back in the queue, giving us a built-in retry mechanism. Huzzah. However, there is one more flow organizational tactic that helps keep this manageable in practice. And that is to isolate your side effects. If you noticed in the flow from earlier, the last step that we do before batching and acking the message was to commit the side effects. The reason for this is pretty simple. Side effects are mutations, and if something goes wrong in a mutation, we need to be able to roll it back. And in the spirit of keeping the flow simple, we batch all the side effects together and put them at the end so that nothing gets lost if we need to roll it back. For completeness, I also wanted to mention that there's another strategy for pipelines where you can't isolate this, and it's called Sagas. The Sagas pattern is a way to handle long-lived transactions, providing like rollback instructions for each step along the way. So in case it goes bad, it can just run that function. I'd recommend anyone to read it. There's a paper on it. I know it's like 10 pages. It's easy to find. It's pretty interesting, especially in this distributed world. There is also an Elixir implementation of Sagas called Sage. But I haven't used it, so your mileage may vary. I just wanted to put it out there so you didn't think that I was just saying, hey, put all of them together, because there's definitely cases where you couldn't put all your side effects together and you need a different strategy. Talking a lot now. Let's take a quick breath. Okay, so far we've covered letting flow do the work and organizing our flow. And now, to be perfectly honest, these two lessons will get you pretty far. But when you're really ready to impress your friends or your boss, then it's time to crank up the throughput. It's time to tune the flow. Now, I wish this was the part of the talk where I tell you that one weird trick to make the flow blazing fast, but alas, I cannot. How you optimize your flow is very dependent upon the shape of your problem. But what we have learned is how to measure flow performance, what are the things that we can actually do to tune it, and then how can we help outside of the capital F flow. So I'll touch on each of these briefly, starting with measuring. First things first, we're gonna need some graphs. Well, we're gonna need some data first, and then we're gonna make some graphs. And since I'm a very lazy programmer, I totally blatantly stole this procedure from a very useful blog post by Timon Tobolowsky, I hope I said that right, titled Measuring and Visualizing Gen Stage Flow with NuPlot. And this is cool because there was a lightning talk on NuPlot last night. I wanted to see if I can put these together now. But essentially involves putting in some function calls at key points in your flow that end up casting out to a gen server which logs the data. And then we just take a given set of messages and zip them through the flow. Then after that test run, we can grab the data that was generated, run a NuPlot script over it, and get ourselves some sweet graphs. Now this gives us a nice sort of like measure, tweak, learn framework for tuning the flow. Okay, so now that we know how to record and measure what's happening in the system, we can start to tweak it. But how? This is where it helps to know a thing or two about how gen stage is used under flow. Okay, so back to our main flow here. Under the hood, flow is actually breaking this up into 3 gen stages. It's more than 3, but it's 3 sections of gen stages, let me call it. Okay, so at the top, we have our producer, which actually is a gen stage producer. And then our middle section is essentially a producer consumer doing all the work for the flow.maps there. And then from the partition on is essentially a consumer, and that's what flow does under the hood. And it's at the boundaries of these is where we can really experiment. That's why I bring them up. So those are the points that we can pull some levers. And that first lever that I want to talk about is max demand. This is how much demand or how many events your system will request from the producers. There's also min demand, but I'm just going to focus on max demand. José had a great talk about min demand and max demand yesterday. So any of the flow functions that operate at those gen stage boundaries that I've just pointed out accept a max demand option. That you can look it up in the docs. There's a handful of them. By default, I believe the max demand is 500, which is fine to start, but it's generally recommended that you explicitly set your max demand wherever possible. And by generally recommended, I mean José told me to do that, and so now I'm telling you. That's how we do this. So in the case of our mappers, we want to drop our max demand down to 10 to match the batch size we get from SQS. This way, each demand of 10 corresponds to 1 HTTP request out to the SQS servers. We could turn it up, but that would mean us waiting on the producer. We would request 500, and then we'd have to wait on the producer to make a bunch of round-trip network requests to fill up that demand before it started passing it down. And we would rather just start processing those messages as fast as they can get it. I'll show you a way around that in a second, too. Our consumer, on the other hand, is a different story. We're essentially, I want to be perfectly honest with you, this partition and reduce combination here is a way, sort of a hack to get Flow to do some batching for us. So in order for it to work efficiently, we limit the partition to one stage. This also means that what that means is we can then jack the max demand way up to like 1,000. And that reduces the communication overhead between the mappers and the partition reducer consumer. They all just funnel into this one here. Now, stages are the other primary lever that we have to tune our flow. The stages option controls how parallel your program runs, basically how many gen stages get spun up underneath. So by default, this option is set to the number of schedulers online in your VM. And this is usually the same as the number of cores you have, or like logical cores on your machine. And you saw in my observer charts earlier, this MacBook had 8. So the rule of thumb here is that if your code is more I/O bound than CPU bound, then you can just crank those stages right up. The trade-off being that more stages incur more communication overhead. There's more subscriptions and demand dispatching and all that going on with more stages. Now, in our case, the mappers here, the producing consumer, are very I/O bound. It's mostly doing database lookups and making decisions and some database writes. So we can bump our stages up. And as you can see, I put in 100 there. Why did I do 100? Well, because the graphs that I showed earlier told me that 100 is where our use case stops seeing the benefits. So that's sort of something you had to measure and feel out and learn. Okay, the final sort of performance lever that I'll mention here is, again, straight out of the performance discussion section of the Flow docs. Did I mention Elixir 1 on developer happiness in our tests? So we want to avoid single sources. So remember our SQS Producer function at the start of the flow? If so, you recall that it can be configured to spin up an arbitrary number of SQS producers. That's what we do here. And I just put up the function call because the config file is not very pretty. This is slightly better. Now we may be limited to requesting batches of 10 from SQS, but that doesn't mean that we can't have lots of producers all asking for 10. That's sort of the shortcut around that. Okay, now if you are like us, then you use Flow in production with a lot of data, you'll find that your bottlenecks in your pipeline are not usually from capital F Flow. We've run into a few occasions where Flow is processing data so fast that it's our dependencies that we needed to tune. The two most common examples of this that I'll just touch on are database connection pools and HTTP connection pools. In our case, those are essentially the two external dependencies, how we talk to our dependencies. Now for both of them, again, it's subject to your system, but essentially I would tune those up as high as you can without seeing any detrimental effects to your system. The higher you can go, the more you can get out of the way and let Flow do its work. Okay, quick review on these main lessons today. First of all, like I said, let Flow do the work. Flow and GenStage are fabulous libraries. We also want to organize our flow to take advantage of those amazing libraries. And then we finally want to tailor our flow to our use case to squeeze all the throughput out that we can. So what else is there to know? These are by no means all the lessons that we've learned from Flow and GenStage, but I think these three cover a lot of ground. Here are a few other lessons that I'm happy to discuss if you want to grab me during the rest of the conference. That first one, José talked about yesterday, and it's just sort of solved, so I got a good answer for that one. Oh, look at that. I have some time left. So, surprise. Bonus talk. Given José's keynote yesterday about Broadway, it's very topical. So everyone, welcome to lessons from our first, 1,000 messages with Broadway. So at Change, we are not running Broadway in production at this moment, but I did start a branch where I converted that flow pipeline that we looked at earlier into a Broadway pipeline, and I'm starting to do some performance comparisons and compatibility things, make sure it's all good. Now, since Broadway is super new, I thought it would be fun to jam in at the end of this talk what it would look like to do that here. So this pretty much, wait, I'm in Europe. Can I show memes? I'm a little worried. Don't tell anybody till I leave town. This pretty much sums up my experience with Broadway so far. Which shouldn't be too surprising. When José talks about how Broadway was born out of seeing how people and companies use GenStage, guess who one of those companies was? So it's very tailored to what we're trying to do. So, like I said, I wanted to convert that flow pipeline into a Broadway pipeline, or should we call it a Broadway Performance? Or maybe a Broadway Production? I don't know. Naming is hard. I think it should be Performance. I'm just saying. I'm putting that out there. Anyway, to switch over, all I really need to do is create a module that implements a Broadway behavior and adds 3 functions: start link, handle messages, handle batch. And I'll show you what I did to make those work. So start link is essentially, this is the same pipeline that I've been talking about this whole time. As you can see, there's the producer section, the processor section, the batcher section. Those map directly to the producer, producer consumer, and consumer sections in the flow-based pipeline that I was speaking on. The other thing to note, just as a sort of a side note, is that I swapped out our custom SQS Producer for the Broadway SQS Producer, and it was very easy to do that. They're very similar, and it was only a little bit of code to swap that out. But now I can delete a bunch of code. That's all I ever want to do. It's great. So this is what I put together for the handle message section. All of our mappers live here. This is literally all the same stuff that was in the flow.map section. The only thing that's different is at the bottom I just put in a case that matches on if the status after all of that is error, then we call it should be Broadway message. I aliased it in the code. We call message.failed, and that essentially tells Broadway to not acknowledge it and just let it go, and we get our automatic retries still. But if the status is not error, we have other statuses I didn't talk about besides OK and error, so we just match on error. But if it's not that, then we update the data that's contained in the flow. I actually just swap out our internal message struct and plop it into the data attribute on the Broadway message struct. Message is totally overloaded in this. I'm sorry if everyone gets confused. But yeah, it's super easy to put that together. But not as easy as handle batches, because it's just passing them through. That's all we need to do. For our particular use case, we don't do anything special with the batches. There's no different partition keys or anything that we need to put it on. All we want are groups of 10, at least 10 or less, at least every 5 seconds at the most. So that's handled in the start link section, and so this one actually just becomes a pass-through. So far, Broadway's looking pretty good. But let's go a little bit deeper and compare some supervision trees. Snow, love me some observer screenshots. These 2 screenshots, on the top you can see one is a supervision tree, the flow-based solution that we put together, and the other one is the Broadway supervision tree. As you can see, all the main points are covered here. We've got the processor supervisor, the SQS supervisor, the thing I haven't talked about yet, but José talked about yesterday, the graceful terminator, which I love their terminator name better. We just call it flow producer shutdown. A little more boring. But anyway, the one thing that's different here is you might notice in the Broadway there is a batcher partition supervisor, which we don't use, but that's because this particular flow doesn't need it. We do have about 4 or 5 other GenStage-based flows that we use, and when I convert one of those, there's one that has much more complex batching, and it's going to fit right into this. So what does all this mean? Essentially, by implementing just those 3 functions, we tick a lot of boxes. We get an SQS Producer with acking, just done, check. We get time and event count based batching, check. And then we get graceful producer shutdown, check. Which I think José had a good explanation of that, but that is a thing that I kept coming to him with questions about because I don't want to lose messages, and it's really useful. But wait, there's more. Everything I talked about in lesson 3 of tuning the flow still applies here. And if anything, it gets a little bit easier. If you look at the start link function, we're defining the max demand and stages for all of the underlying gen stage boundaries. So in the producers section, we use the stages to set up the number of producers we want to spit up. Like I said before, we pass it in as a config, so we pass it in as a config here. In the processor section, we define our stages to match what testing determined was best. So there's our 100. You'll note that I didn't define a max demand there because in Broadway, the default for this is 10. Must have thought SQS would be involved. So that's what we want, so I didn't define it there. And then the one slight difference is in the batches section. The number of batching stages is defined by the number of batch keys present in the system. And like I said, in this, we don't have any complex batch keys, so there's just one. So that is defined not by us, but by Broadway. But if we were to add a stages option, you can still send one in to the batchers. It's actually for the number of consumer stages, like batch consumer stages. In our original flow pipeline that I'm replicating here, we only had one batch consumer stage, so I left it as that here, although this is a very possible optimization that I will have to measure and get back to you. On our flow one, for anyone that's curious, you could then, after all the batching and acking, you can, or just before the acking, you could even do a flow.shuffle, and that will re-parallelize it from the one stage that it was in. And in this, you just define stages here, and you get the same thing. One last thing on the batcher section is that you can see that we can define the batch size and the batch timeout. Before we had to put that in our window function and then it was higher up in the code. It wasn't like right front and center, but here this defines the exact same thing. So give us batches of 10 or every 5 seconds. Get it done. Okay, folks, thanks for letting me share that with you today, and thank you for humoring me as I jammed in a Wildcat talk there at the end. If you can't tell, I am pretty stoked about Elixir generally, and also excited about its potential in the data processing field. GenStage, it's such a good foundation, and the abstractions on top of it, both Flow and Broadway, are a real pleasure to work with, and they're so powerful, it's great. And I would be remiss if I didn't mention that Change.org is hiring, so if you want to come have an impact on social change around the world, check out that specific link. So thank you, and Jekui? I'm not very good at Czech, sorry. We can do some questions.
Great. So we might have time for one question maybe. Does any questions? Questions posed as comments?
There's one hand there.
Oh.
Hi, thanks for that. It's really interesting. Just how do you handle your errors and retries in the flow before you go to Broadway? And do you have any issues with duplicates being reprocessed, things like that?
So in our use case, we've put in, maybe one of the functions that I left out of that is, specifically with SQS, they give you a unique message ID, and we end up verifying that against a sort of a short-lived Redis list or set, and we see if it's in there, and we will block it if it's not. We also, in our use case, pass successful messages onto another system, and that does the same thing. So it's just sort of in there because it's a at least once system in SQS.
All right, looks like we're ready for the little bit of a short break to switch here. Let's thank John one more time.